Okay, so welcome everybody. Thanks for coming. So this is we are having a SMU colloquium. This will be by Rajesh, who is our visitor for the semester. As you know, Rajesh is from ECE IAC. So he'll be speaking about 4 levels of fixed point analysis. So two things. So if you have any question, actually, please feel free to unmute yourself and ask the question, or you can post it on chat, and we will also have some time for questions at the end of the talk. Okay, over to you, Rajesh.
Thank you. Thank you for the invitation to give this colloquium and speak about 4 levels of something called the fixed point analysis. And the fixed point analysis is a tool that has been used in many communication networking problems in performance analysis of communication systems. So underlying the fixed point analysis is this notion or a notion of self-consistency, and I would like to describe that. So suppose we have a system of n identical interacting particles, and these particles interact via what is called the mean field. So the mean field is if you have these n particle system, you look at, and they have some states, look at the empirical measure of their states. That would be the mean field. And any interaction that happens between these nodes is through that mean field. So one way by which people go about analyzing this system, it's a sort of shortcut to analyzing the entire system or a full analysis of the system is the following. So let's say that there is a generic node and this generic node has a behavior, and let's call the behavior B. We will attribute by symmetry the same property B to all the nodes. Additionally, we will also attribute independence across all these nodes, and therefore each of these has this particular property. What it is, it will become clearer. What this independence is will become clearer as we go along. So there is a system then with n particles, each of them having this property B, and think of them as possibly probability distributions. They are independent across these particles. This sort of leads to a mean field, and that mean field then governs the dynamics in a certain way. What we do to analyze the system or to come up with a shortcut analysis of the system is we pull one out, or we tag one of the particles and look at the tagged particle. And we see how this tagged particle responds to the mean field. So here is a particular initial behavior that you started with that created the mean field, and you're examining how one particle responds to this mean field. And so that's a function of this original behavior that you started with. Let me call that as T of B. So it's the outcome behavior or a response behavior to a mean field that comes from B. Self-consistency demands that this response behavior T of B to the initial B must be B itself, because B itself was one of the particles that comprised the system. This is the idea of self-consistency, and you get a fixed point T of B equals B. So it's a fixed point for the map, which is the response map T to a particular initial. So we will see this at 4 different levels as we proceed in this talk. So that's just a quick overview of what is to come, mean field fixed point analysis, and the self-consistency requirement that underlies this fixed point analysis. So I'll now give a concrete engineering example so that the ideas that I present here can be understood with respect to this example, and that will be the mean field interaction in the wireless local area network. It's a somewhat classical system, but I will describe this, and it's somewhat easy to understand, so it's a good example to work with. The wireless local area network is an interesting example because it's a protocol that has been developed in a distributed system to enable coordination across these nodes, so that some common goal, which is each of these must communicate with some wireless access point. So that coordination is somehow achieved. They don't step on each other's toes, or at least the stepping on each other's toes is minimized to an extent possible by coordination. So it's called the distributed coordination function, and the 802.11 protocol, it's a protocol that the IEEE has. It involves a countdown, but what I will do is I will describe a Markovian caricature of this, and we look at the analysis. Okay, so in this particular wireless LAN, there are n nodes, and I'm going to discuss only the simplest wireless LAN. There are n nodes that are accessing a common medium. We will assume that they have an infinite backlog of packets, so that there is always some packet to send. And at each slot, the consideration is for sending the first packet in the queue, which is called the head of the line packet. HOL stands for head of the line. So if a transmission is attempted, it's going to be for that particular packet. Each node also has a state, and we call this the backoff state. And the backoff state can be either 0, 1, or up to m-1. And I'll give you an interpretation for this very soon. But what this backoff state determines is what's the attempt probability when you're in that particular state. So if you attempt with a higher probability, you're a little more aggressive. If you attempt with a lower probability, you're less aggressive. The backoff state determines the aggressiveness with which a particular node will attempt to transmit its head of the line packet. The states, here are the states 0, 1, all the way to m-1. The transitions are as follows. So you can be at 0, and you can remain at 0 after a transition. Or alternatively, you can go to 1. From 1, you can go to 2, or you can jump back to 0. In general, from I, you can either go to I plus 1 or jump back to 0. Okay, so that's how these transitions are. The last state is special. You don't have a higher state, so there is no upward transition. You just remain there if there is a need to go ahead. So what do these transitions mean? When a particular node is, so let's say that we have a head of the line packet. This number here, which is the state index, it codifies how many times we have already attempted to transmit this particular packet. So for example, if we have a fresh head of the line packet, we have not made any transmission attempts for this particular packet, then we will be in state 0. If we attempt and we succeed, then the packet is out of the system. A new packet comes and becomes the head of the line system. And that's when we transit from 0 to 0. We are back in state 0, but this time the 0 corresponds to a new packet. If we attempt and we fail, then we have attempted once and we have failed. So this codifies the number of failed attempts. So that means we jump from 0 to 1. We have attempted this particular packet once and we have failed. If we attempt once more and we succeed, then this packet is out of the system, a new packet comes, and so we come back to 0, because for the new packet it's 0. But if we fail, we have attempted now twice, so we go to the next higher state. So in general, at I, you can either succeed or fail. If you fail, you go to I plus 1. If you succeed in transmitting this packet, you come down to 0. So that's about packet successes and failures and how they tell us whether we will go to the next higher state if we fail, or go to 0 if we succeed. Now, how do we go up to the next higher state, or how do we succeed? That's where the interaction between the nodes come in. The interaction is as follows. If in a slot 2 nodes simultaneously attempt to transmit, then they're both accessing the medium. There isn't enough signal to noise ratio, that's what we call it, to capture the packet. And therefore, there is a collision, and this particular packet remains in the queue. That's the situation when the packet transmission has failed, and each of the nodes then jumps to the next higher state. On the other hand, if there's only one node that attempts to transmit, then this transmission succeeds and the node jumps to state 0. So that's the interaction between the nodes. Okay. So this is as far as this wireless LAN system and interactions are concerned. I'll now give an example design. How do you choose the CIs, etc.? So I'll give one example. So assume that there are only 3 states, 0, 1, and 2. And the attempt probability for a node in state I will write it as some number Ci divided by n, where Ci depends on the state I. The Ci actually codifies the aggressiveness of the transmission, as I already described. And the scaling by n is to ensure that the overall system attempt probability is of the order 1. So if you notice here, if the attempt probability for a particular node is Ci by n, then there are n nodes in the system. Then if you look at the overall attempt probability in the system, it's n times Ci is of the order 1. So n times Ci by n, an upper bound on Ci, let's say, by n, and therefore that's of the order 1. So that's the reason why one might want to scale the attempt probabilities in this way as the number of particles or number of nodes in the wireless LAN system increases. Otherwise, there are likely to be too many collisions. The conventional wisdom, and this is where the design aspect comes in, is to choose the aggressiveness to be 1/2 of the aggressiveness in the previous state. That is to say that if you succeed, you go to state 0, you have a certain aggressiveness there. But if you fail, then the attempt probability is 1/2 of the previous attempt probability. That means you're more polite, you transmit less often. So what this does is it doubles the waiting time after every failure. Nodes are increasingly more polite as they go along. But this is not too much of an issue because once a node succeeds, it gets the opportunity to transmit at the higher rate. So it's fair to all the nodes, but it is possible that some nodes might remain in this aggressive state for a long time. Those are all questions of fairness, etc., that we are interested in, but I'll not speak about it here. So that's a design that
I had a small question.
Yes, please go ahead.
After a failure, the state I will go to state I plus 1. Is that correct?
That is correct. If a node attempts to transmit and that transmission attempt fails, that node state moves from I to I plus 1.
And this happens at rate C sub I, with the probability of what the failure is.
No, every node, what happens is that there is an attempt to make a transmission. If the transmission attempt doesn't happen at all, then you remain in that state.
Okay, thanks.
I have a question also. So can I ask?
Yes, please go ahead.
So in the last state, you have put a self loop, so it will stay there, right? Is that correct?
Correct. In the last state, if you happen to fail there, you could have higher and higher states, but the meaning of this, you remain there, is the transmission attempt rate for all those higher states assume that they are the same. One could effectively think of that as just the last state. The number of attempts is bigger than or equal to m minus 1. That's what that is.
But another question, so this interaction, if multiple nodes try to transmit, nobody transmits, right?
Correct.
So
yes.
As opposed to say, I can have a model where one of them randomly transmits and it's slightly better or less wasteful, but maybe not substantially.
Yeah, there are such nuanced models as well. There are these are called capture models in our literature, where you can actually look at the signal to noise ratio and try to make the best out of the packets, and you do succeed with some probability. I don't take that into account. In my simplified model, if two transmit simultaneously, I just assume that there is a collision and make them both go to the next state.
Okay.
Yeah, this for a simplification. Okay. Let me proceed further. I now want to describe this fixed point analysis and a fixed point at the first level, and that level is at the level of macroscopic observables. And you will see that there are parallels with statistical physics, and some of these parallels are actually quite exact. All right, so observables in our example will be collisions and atoms. Let's begin with an observation about these observables. The observation is about, not about these observables, but about the interaction. If you look at the possibility of a collision for a particular node that's attempting to transmit, this probability of collision for this node will depend on the states of the other nodes. If all of them are in state 0, for example, then your chance of success is small because those nodes are transmitting at a somewhat aggressive rate. But one symmetry that we have is that it doesn't depend on the node IDs. It also depends only on the empirical measure. So we recognize this particular symmetry. So the collision probability for a particular node doesn't depend on the exact states of the other nodes, but it depends on those states only through the empirical measure. All right, now you take this empirical measure. Actually, you have to think about when you're transmitting what the empirical measure is of the other states. So it's the empirical measure of all the other states except. So let xi be the current empirical measure of the nodes across states. That means there are n xi0 nodes in state 0, n xi1 nodes in state 1, and so on. And let's say that you are in state 0, then there are this many others in state 0, and then state 1, state 2, n xi1 in state 1, and so on. So I'm just subtracting 1 from the number that are there in state 0 because this node is included. Now we ask, what is the chance of success if I were to transmit, or if you were to transmit? So you're in state 0, you attempt to transmit. For you to succeed, nobody else must transmit. What's the probability that that happens? If you assume there's independence and each one transmitting with probability Ci by n if they are in state I, you can write this as nobody who's in state 0 must transmit. So the chance that one of the nodes in state 0 doesn't transmit is 1 minus C0 by n. And there are this many of them, so you raise it to that power. And do the same for all the other nodes which are in different states. For each state, there are n xi number of nodes in that state. And that gives you the probability that nobody else transmits in this particular slot when you're considering transmission. We can symmetrize this. It's asymmetric because I've considered your state to be state 0. We'll symmetrize this by removing the -1, and then we have this expression. And we'll pass to the limit as n becomes large. So then this is approximately e to the minus xi ni and a product. And that just gives me e to the minus the inner product between C and xi, where C is the aggressiveness and xi is the current empirical measure. And of course, the first term is negligible because as n becomes large, this goes to 1. So one thing that you will notice here is that this probability of success doesn't depend on the node, on your node, which is under consideration, your state. And therefore, it is the same for all states. It's e to the minus the inner product between Cz. The inner product between Cz also has an interesting interpretation. You can think of it as an activity parameter. In fact, it's the expected number of attempts in the slot, because the inner product can be written as xi ci summation over I, and we just multiply and divide by n and recognize that n xi is the number of individuals in state I, and ci by n is the attempt probability for each of those nodes. And so the expected number of attempts across all the states is just to take this product and sum it up. And that's just the inner product. So e to the minus the inner product gives you the probability that nobody is transmitting in this particular slot. And it has this interpretation of an activity coefficient or an activity parameter. It's the expected number of attempts per slot. Okay, I'll now go to describe the fixed point. So broadly, the fixed point involves recognizing a particular property and then assigning that property into a mean field property, extracting a particle and doing an analysis of how that particle responds to the mean field, and then saying that these must be one and the same. So let's see how to execute that here. Suppose we have a conditional, suppose you're planning to attempt. So the conditional collision probability for a node that is just about to attempt, let's say it's thinking of attempting, we are looking at what the collision probability is. We just saw that it is independent of this particular node state. We can also say that because of the symmetry across the nodes, that it doesn't depend on the node. It's the same for every node. So let's take this. So this particular talk will be full of heuristics. In fact, there is no rigorous results that I will state, but all the things that I say can actually be made rigorous. But I'll stick to the level of ideas and then describe only heuristics here. So the collision probability, we can, let's say, assume that it's the same for every node and it's independent of the state in which that node is. That's given by 1 minus the probability that there is no collision, which we saw in the previous slide was e to the minus the activity coefficient. So that's 1 minus e to the minus the expected number of attempts per slot. Okay, so we'll call this gamma. Now let's say that this sets the field. So we'll assume that under this field, so each node now attempts to make a transmission and it might have a collision. And this collision probability is set by the field, and that's given by this gamma. Let's see what happens in order to analyze how this particular node would respond to this field. Let's focus on one of the nodes. We are going to tag a node and look at its behavior. And we'll analyze how that particular node behaves. One thing to recognize here, which eases the analysis, is to see that there are actually renewal instants in the evolution of this particular particle's trajectory. And one particular renewal instant could be when it returns to state 0. Every time a return to state 0 indicates a successful transmission, a new packet has come in, and then you go through a cycle. So you may try to transmit this, you fail, you go to the next state, and so on. Ultimately, you succeed, and then you come back to state 0. And every time you come back to state 0 and start a new packet, that's like a cycle. So those are renewal instants, and we'll actually use these, look at these renewal instants and use the renewal reward theorem to write down what the expected number of attempts for this particular node is. Now, the left side here, all the way here, is the expected number of attempts for this node. There I use symmetry, where I say that, well, there is an expected number of attempts for the entire system. There's symmetry, so this particular node's expected number of attempts per slot is going to be 1 by n of that. So let's begin with that. Now I write down this expected number of attempts per slot in a different way using this renewal reward theorem. And there I focus only on the cycles. I look at one cycle, I find out what the expected number of attempts is in that cycle. That is the numerator here, expected number of rewards. And then I look at the expected cycle time, that's the denominator here. Okay. So these are easy to get in this particular instance, given the considerations that I will speak about now. So how do I get the expected number of attempts? Or this is the reward in one cycle, expected reward in one cycle. Well, I must make at least one transmission, that's this. But with probability gamma, I might have a collision and I must make one more transmission. So think of this as gamma multiplied by 1. But with probability gamma square, I must make one more attempt and so on. And of course, there is a special handling for the m-1 that needs to be brought into the picture. But that's a matter of detail that I will not get into. It can be done, but I'll not get into that here. So you see that this gives me the expected number of attempts per cycle. And then what is the expected cycle time? Well, the attempts, the number of slots I stay in state 0 is governed by my attempt rate at state 0. And that's geometric with probability C0 by n, because I'm attempting with probability C0 by n in that particular state. And the expected time in that state is then the inverse of that, that's n by C0. But with probability gamma, there is a collision. And then I go into state 1, and there I remain similarly geometric, but this time C1 by n, and therefore the expected time is n divided by C1, and so on. So you see that this can be written as something which is a function of gamma divided by n. And by the symmetry property and this renewal reward analysis, we can actually knock off the n and see that the activity coefficient, which is the expected number of atoms in a slot, is actually a function of the collision G of gamma. And this was based on a response analysis for this particular node. Now, here we have the collision probability as a function of the attempt and expected number of attempts. And here we have the expected number of attempts as a function of the collision probability. And therefore, we can write this as a single fixed point in one of the variables, and we choose to write it in terms of the collision probability. Gamma is 1 minus e to the minus attempt, and attempt is just g of gamma. So gamma is 1 minus e to the minus g of gamma. And so we can solve this and hope that the system will actually operate at a solution to this particular fixed point. So here you can see that the solution depends only on the parameters C0, C1, etc. for the attempt probabilities, and a certain gamma which is unknown, which I want to discover, and I discover that by solving this particular equation. So that's the fixed point. We solve this, and we hope that the system will be there. One thing that I would like to highlight, in fact, I would like to highlight two things here. The first one is that we have actually analyzed the system without actually doing a full-fledged analysis of the Markov process. What we have done is we have extracted some properties and looked at some invariances and identified some consistency conditions, and go solve it, and you know exactly where the system operates. And the system has this particular collision probability, and it's a collision probability that is easily measured. you can check, for example, how much is the how many times you see a high energy in the system, and that's and you can focus on one particular node and see how many times it collides, and that is an observable. Similarly, the number of attempts by looking at the energy is also something that you can measure. So these are consistency conditions that relate some macroscopic observables, and that gives us a simple way to analyze the system. So that's the first point that I would like to make. The second point that I would like to make is something that us engineers are worried about. We would like to make this gamma as small as possible, for which we have to choose. Now we are engineering the system, so we would like to choose the C0, C1, etc. in an appropriate way. So there's a quick way to see where the system would be, and we try to see whether the C0, C1, etc. can be improved. So that's a different goal. When we wear the hat of the designer, we go and look at it. But when we wear the hat of the analyst, and today that's the hat that we will wear, this is what we will stop at. Okay, so that's at the level of macroscopic observables. Now I want to think about or describe other levels of fixed point, for which I will move from the discrete time version to a continuous time version. And I'm going to speak about a certain continuous time Markov chain with weak interaction. It's not an exact replica of the model that I just described, but it's close, and one can show that the limit laws associated with these are essentially the same. So I'll describe the continuous time caricature of this discrete time system. So I must describe the coupled dynamics to describe the system. So let's begin with that. First, what I do is I go from the discrete to the continuous in the following way. I embed my slot boundaries for the discrete time system in R+, and I endo a duration of 1 by n for each of those slots. That's the first step. Then I recognize that the transition rates, which are essentially the probability that you change in a particular slot from one state to another, divided by the slot duration and pass to the limit. So that would be the transition rates. They are of the order of 1, because the attempt rate is of the order of 1 over n. And then you might change to one of the states, that's of the order 1. So overall, the numerator is of the order 1 over n. But then the denominator, which is the slot duration, we just set it to 1 over n. So that gives us a transition rate of 1 over n. The transition rate for success or failure, as we saw in the first example, depends on the mean field, the empirical measure. And let's write that mean field as mu n of t at time t. I'm also indicating that it depends on the number of particles n. So mu n of t is the empirical measure of the nodes across states. And at time t, we write down now the transition rate. The transitions were I to I plus 1 in our example, and I to 0. Those were the only two transitions possible. And so the I to I plus 1 transition rate, let's write it as lambda I plus 1. And we'll also make it a function of the empirical measure to say that there is a mean field interaction. Similarly, I to 0, the transition rate is denoted as lambda I0, and it's also a function of the empirical measure. In our example, these were the only two transitions possible, but in general, you can have other transitions as well. And so we'll in general write it as lambda ij, function of the empirical measure. Okay, what are these lambda ij's in our example? It's fairly straightforward to write it down. So let's look at 0 to 1. That means a node in state 0 transits to state 1. What's the rate at which it transits? Well, it must try to make an attempt. That happens with probability C0 by n. Nobody else must attempt. So the probability that that happens is 1 minus the probability of, I beg your pardon, I'll go back and describe this again. It must make an attempt, and for it to fail and go to state 1, somebody else must transmit. That means there must be a collision, and this was the collision probability. And this happens in slot time 1 over n. And so we can write down the transition rate as C0, the n cancels off, and it's C0, 1 minus e to the minus the activity coefficient, which depends on the empirical measure. Like this, we can write down for all possible transition rates, and we can write it in the form of a matrix, and it looks like this. We just saw how to compute this. These terms are also similar. And here, this is the transition for a success. So Ci by n is the probability that you transmit in state I, and you must succeed. That means nobody else must transmit. That's e to the minus the activity coefficient. And so that's the rate at which you jump from state 1 to state 0. Similarly, state 2 to state 0. For today's exposition, we will actually assume this particular continuous time caricature with these instantaneous transition rates. But I would like to highlight one important difference between this system and the previous system where the interaction led to transitions. In the previous system, you jump states only in conjunction with another node that's transmitting, and both of you fail. That means that two nodes transit at the same time, or two or more nodes transit at the same time. Single node transitions are associated only with successes. When you're the only one that's making an attempt to transmit, then you go to state 0. So we do have multiple transitions at certain instance in the discrete time system. But in the continuous time system, if we pass to this particular rate system, then you actually don't see these multiple transitions of going up, which are the failed transmissions. Nevertheless, one can analyze this and one can show that the two systems are close to each other in terms of the limit loss. So I will focus on this particular system. I'll now try to describe a level 2 fixed point, and that's at the level of distribution over states. Okay, suppose we have a generic node that we look at in the system, and the generic node has a probability of being in a particular state given by a probability distribution xi. So this captures this particular generic node's behavior, so to speak. And by symmetry, we'll assume that all the nodes have this behavior and they're all IID. This leads to a field. And the field in this particular situation also happens to be the measure itself, the distribution over states. And that's if the probability distribution of being in a particular state is given by xi I, the ith component of a probability distribution xi, and you have n such things and they are all independent, then the field, the empirical measure, is also given by this as n becomes large. And now we'll look at one tag node, we'll isolate this node, and we'll see how this node responds to this equilibrium. And the notion of response that we will have is we will demand a certain local balance. Okay, so the response is T of xi to the field, which will be a probability distribution m. So I take this xi and I respond to it, that is T of xi, which is a particular m. So what property does that m satisfy? This m must satisfy the exit rate from a particular state k that's given by this. Oh, sorry, this is the entry rate into state k that must match the exit rate into. So this is the transition from some other distribution, some other state, and you're transitioning into this particular state k. So mi is the probability that you're in state I, lambda ik is the probability that you transition to k, and this is the rate of the transition. So the net in rate must equal the net out rate. So that's what we will demand. And we look for an m that satisfies this. Another way of writing this, or this is true for every state. This is one equation for a particular state k. We actually have to impose this condition for every state k. And when you do this, you can actually write this condition or this requirement in matrix form as m transpose lambda of xi equal to 0. And so what we are looking for is an m that solves this equation. That m, which is a solution to this equation, I'll call this as T of xi because it depends on the xi that we start. The self-consistency demand is that this response T of xi equals xi. And therefore, instead of looking now at collision probabilities, etc., which are macroscopic variables, we can look at distribution over states and demand this particular response at equilibrium. And that response at equilibrium satisfies this fixed point T of xi equal to xi fixed point equation, which one can write as this. And so the only emergent xi for the system are those which satisfy this particular equation. We'll see this and interpret this a little better in the later slides. But this is the fixed point equation at the level of distribution over states. Now one might ask, what is the connection between this level and the first level, which is at the level of macroscopic observables? So here is the connection. So take a xi that solves this particular fixed point equation, that is xi transpose lambda of xi equal to 0. And we now have a xi that solves this. Let's look at the attempt for this, which is the expected number of attempts per slot, or the activity coefficient. Then what we do is focus on a particular tagged node and compute the collision for that. And that's going to be 1 minus e to the minus this activity. It's the same regardless of the node state. What we then do is compute for this collision g of gamma. And we verify that gamma is equal to 1 minus e to the minus g of gamma. So in other words, the xi that we get from the level 2 fixed point actually solves the fixed point condition for the level 1, which is at the level of macroscopic observables. So in other words, all the macroscopic observables are coming from this particular microscopic distribution of states. So you can see here the similarity to an ideal gas, max xi being similar to the Maxwell-Boltzmann distribution. And this equation that relates gamma is equal to 1 minus e to the minus g of gamma, an equation like PV is equal to nRT at the level of macroscopic variables.
I have a question.
Temperature. Go ahead, Shiva.
Is the lambda the same as the example lambda that the one that you took here?
I think you mean gamma or lambda?
No, the capital lambda at the top.
This lambda, yes.
Yeah.
So this lambda, you must have exactly this example lambda.
Example lambda. Very good. Okay. Okay.
Yeah,
it's not general. Yeah, very good. Okay. That's okay.
So the specific equation will depend on the nature of these equations, and the nature of these equations determined the g of gamma function, etc. So that this is specific to that particular.
So is this to understand correctly that the second model is kind of more general than the first discrete model?
Correct. Yes, and I have specialized it to that particular interaction rate function, the transition rate function.
Okay, very good. Thanks.
Okay, yeah, thank you. Okay, I'll now go to the next level, which is at the level of dynamics, specifically measure valued flows. So this is the level 3 as I have presented. So this builds on the previous setting. The previous setting had xi's and m's. Xi is both xi and m were probability distributions on Z, which is the set of states. Now we have actually measure valued flows over that state space, xi dot and m dot. Okay, how do we go about coming up with a fixed point here? So let's once again look at evolutions of these particles, and let's attribute a property, and this property now is generic node's evolution of the probability distribution, and that is xi dot. Okay, so let's take this, and then we'll give it to we'll endo all the other nodes with this property. We'll assume that all the nodes evolve in exactly this fashion. That's symmetry. We'll also assume independence, and that gives us a certain field. And the field in this case is also xi dot, the measure valued flow across time. So if I have n IID particles evolving according to, let us say, a xi dot measure valued flow that describes their marginal probabilities, and they are independent, and I'm looking at the empirical measure of the states and its flow, in the limit, that's also going to be xi dot. So we use this law of large numbers argument to say that the field is also going to be xi dot. And now we consider one tagged node and see how it responds to this field. So I call that response as T of xi, and remember that the response must also be a measure valued flow. So that's an m dot, which is a response to the xi. So that's why I call it this, but it's an m dot which satisfies some condition. And the condition is that it's looking at the inflows and outflows in a dynamic way. So dmk of dt tells me the rate at which this particular node enters state k. You can think of it as a time average. You can think of it as the probability mk of t and how that changes with time. Let's examine what that is. So that depends on mi of t, the current probabilities of being in the other states, and then transitions from that state into k. So this would be the inflow rate, this first term. And the second term is the outflow rate. And the rate at which mk of t changes, dmk by dt, is the inflow rate minus the outflow rate. So we just write this down. I'll connect it with Kolmogorov forward equation a little later. But at this stage, I'm just asking that the dmk by dt match the inflow rate and the outflow rate coming from the mean field. And the mean field tells me what the transition rates are. And the mi of t is the probability that I am in state I at time t. Another way of writing this is to write it in exactly the Kolmogorov forward equation sort of way, where we write it as dm by dt is equal to m transpose lambda of xi of t. Okay. Now, t of xi is that m, which is a path, a measure value flow that solves this particular differential equation. So self-consistency then demands that t of xi equals xi itself. So yet again, you can see that we have not really analyzed the system in full, but we are saying that the system's evolution in time, or its how the mean field will evolve in time, is something that satisfies this fixed point equation. And if you look at this fixed point equation, plug in m of t equal to xi of t, that's what we are demanding in this particular equation, then that gives us this equation here, which is a nonlinear ODE. This equation is called the Mekin-Vlasov equation, and we try to solve this. So the fixed point at this level, measure value flows, is an m is a xi that satisfies t of xi equal to xi, where t of xi is a solution to this Kolmogorov forward equation for a mean field that essentially is given by the xi. Okay, so that's this particular fixed point. What's the connection between this and the previous one? Well, it's a matter of setting the dynamics to be at steady state. So at steady state, d xi by dt is 0, and that means that xi of t is a constant. But d xi of dt is also xi of t transpose lambda of xi of t if it is a level 3 fixed point. And therefore, we just plug in xi of t equal to xi, and that must be equal to 0, which you will recognize was the condition for a level 2 fixed point at the level of distributions. This is the psi for level 2. Okay, I'll now move to this last level, which is at the level of laws and particularly Markovian evolutions. So let's see how we can get to this particular fixed point. This time, the property or the behavior that I'm looking at is actually the law for the trajectory of a particular particle. So take a generic node, let's call that generic node I, and look at its law, and let's call that law Q. What we will then do is attribute this law to all the n nodes in the system, and those n nodes we will also assume to be independent and identically distributed. And once you do this, there is a field, and that field will induce a certain measure valued flow. So write xi of t. Okay, so we can do it in a slightly different way, and I'll follow what I have here rather than the way in which I started describing this. Take this Q and then look at its push forward. That is the marginal of the ith particle, and the marginal at time t of the ith particle. That is xi of t. What we will do is we'll attribute this xi of t to all the particles, just like we did before. And when we do this, that defines the mean field. And like in the previous example, which is the level 3 fixed point, the mean field is now going to be xi. So here you will notice that there is a difference between the behavior that we are trying to study, where we get the fixed point, and the field. The field is a measure valued flow, but the behavior is a law of a particular particle's evolution. Okay, so this defines the field. Then we look at how a particular particle will respond, a tagged particle will respond to this. So for this, we take the field and get a time in homogeneous jump rate matrix, which is lambda of xi dot. And we look at how a particular particle will respond when the time evolution is governed by these jump rates. So the T of Q will then be a Markov process. It's a response to Q. It's a response to Q through this measure valued flow. So you take the Q, you look at its marginal at time T, look at its flow, that's xi dot, that defines the mean field. And you look at then the time inhomogeneous transition rates given by that field, and you look at a law associated with that. I call that as T of Q. It's a function of Q because it depends on Q. That's just a Markov process with these time inhomogeneous transition rates. So to say that it depends on Q, I have essentially brought the dependence, indicated the dependence in this way. Lambda of xi of t, but xi of t itself is a push forward of the Q at time t, and we are looking at the corresponding law that comes from these transition rates. Self-consistency then demands that this law, that T of Q, must match what we started with. So that is T of Q is equal to Q. Okay, so this is the fixed point at the level of laws. And once again, this is a shortcut way to analyze the emergent Q for this interacting particle system. And the fixed point is now at the level of laws. I'll now relate this to the level 3 fixed point. Okay, before I do that, I want to make a quick connection to martingale problems and what kind of martingale problem this one is. Martingale problems are problems which give a generator, an operator in a operator that operates on functions in a certain space, and then and then you have an initial law and you ask for existence and uniqueness of processes that satisfy a certain martingale property. In this particular context, it is suppose we are given time dependent transition rates, which I call lambda of t. The question is about existence of a Markov process with these transition rates and specified initial conditions. And the martingale property that this particular law would satisfy is that if you look at a particular function f, f of x of t minus f of x of 0 minus the compensator is a martingale. That's what we are looking. We are looking for processes or laws that satisfy this particular martingale property. And are there processes which satisfy this property? Are they unique given the operator and the domain and the initial condition? Are questions that the martingale problem tries to address. In our context, though, if you just look at this martingale problem in our simple context of jump process setting, finite state space, and these rates are all bounded, existence and uniqueness questions are easily addressed. So it's a rather straightforward problem in this particular context. But the particular fixed point that we are looking for is actually looking to solve this martingale problem in the following setting, where the jump rates, the lambda of s, is not a fixed function of time, but it's something that depends on the process itself. And so there is some sort of self-reference here, and that leads to this nonlinear martingale problem. Can I find a process that makes this f of x of t minus f of x of 0 minus the compensator here depends on the x through the mean field? Does this become a martingale? So it's actually looking for certain special Markov processes which have a certain property, and this particular existence and uniqueness criteria for these need to be established, and the nonlinear martingale problem is associated with such questions. Now I'll tell the connection between level 4 and level 3. So level 3 speaks only about the measure valued flow and asks us to solve this differential equation, a nonlinear differential equation, but it's at the level of only these projections. The process itself need not be Markov. For example, the process could come from a hidden Markov process, and this law may yet be satisfied. This condition may yet be satisfied. Whereas level 4 is actually looking at the dynamics of the particle and saying that that must be a Markov process. So it's asking for something more. And so level 4 is demanding a little bit more than level 3, so it's more informative. What is the connection between the two? So what we do is we take a solution to the level 4 fixed point, we project it and get the measure value flow, and then we write down the transition rates associated with this measure value flow. It's a time inhomogeneous transition rate matrix. We then solve the forward Kolmogorov equation for that. But since this is the outcome of a level 4 the Q is the outcome of a level 4 fixed point, the Kolmogorov forward equation for that says that xi dot of t must equal xi of t transpose multiplied by the transition rate. But the transition rate is transition rate matrix. The transition rate matrix depends on the xi of t. And what this equation is the McKean-Vlasov fixed point, McKean-Vlasov equation. And so that governs the level 3 fixed point. And so the connection between level 4 and level 3 is to project it and see what the measure value condition, what condition the measure value flows satisfy. And that connects up level 4 to level 3. So I'll now put down the 4 levels once again.
Rajesh,
Yeah, go ahead. Yeah.
Is there a way to go from level 3 to level 4? If we have the push forward at time 0 and we have the solution to this level 3, is there a way to get to level 4 with macro?
So, yeah, so the level 3 fixed point is basically a xi, a solution, a measure valued flow. One could think of building it's just that in level 3, we never really demanded a little bit more information about the system. So let me ask your question in a different way, and then that might make things a little clearer. Is there a way to go from level 1 to level 2? You can ask that. Macroscopic equation is there. Can I get level 2 from there? There may be many systems that have the same level 2 equilibrium. All of them might have the same level 1 macroscopic equation. So that's possible. But in some sense, the level 1 itself is coming from something that is there, but we have not looked at. It's intrinsic to the system, but it's just that we have not looked at, we have not focused our attention on it. So there is some underlying level 1 which led to this level 2 which led to this level 1. Similarly, I would say here that there is some underlying level 4 which yields this level 3, but there could be many Markov processes which might yield the same level 3 McKean-Vlasov equation. That's possible. I haven't. This would be my response to your question. I don't know if that answers your question. It's just that there is some underlying level 4 that governs the level 3 as well. There may be many such things which govern the single level 3. That's possible, although I need to think about that uniqueness a little bit more. But there is some underlying level that leads to that. Okay. The 4 levels, once again, just to review what we have seen this far. Level 4 is at the level of laws of processes and its solution to a nonlinear martingale problem. Level 3 is at the level of measure valued flows. And it's coming from, you can think of it as a sort of projection from level 4, but it's a solution to a nonlinear ODE system, particularly the McKean-Vlasov equation. It's called the McKean-Vlasov equation in this context. Level 2 is to ask for equilibration in level 3, that is set the dxi by dt equal to 0, and you will get some condition. That's level 3, and that gives us the distribution over states in some sense, like the Maxwell-Boltzmann distribution for ideal gases. And level 1 is at the level of macroscopic variables. It's a function of this xi and gives us some interesting observables that we might have been able to track. So these are in some sense easy to measure, but these are all somehow intrinsic to the system that eventually lead to these emergent observables. And one needs to look a little deeper into the system to unravel each one of these, but they're all related. Okay, what do we need? What assumptions do we need to make all these rigorous? So there are some assumptions and then there are some tools. I'll not speak about the tools, but as far as the assumptions are concerned, to put all of what I have described in a rigorous framework, we need to put some conditions for the level 3 and the level 4 fixed points to hold. And one condition, one sufficient condition is that the nonlinear ODE is well posed, or the nonlinear martingale problem is well posed. So you can put it in either way. The nonlinear ODE being well posed can be guaranteed if the lambda ij, which are functions of the empirical measure, are Lipschitz. So that suffices to ensure that this is well posed. So that's one condition under which you can make all of these results rigorous. But these results, you will notice, are for the finite horizon. So to go to level 1 and level 2, which is essentially something about equilibration, we need a little bit more. We need one more condition, that the initial conditions on the n nodes are exchangeable. Okay? And as you pass to the limit, one can generalize this, but we also want the limiting initial condition to be a fixed deterministic starting point for the empirical measure. As far as the level 2 and level 1 theorem results are concerned, to make them rigorous, what we need is an additional condition that the nonlinear ODE is globally asymptotically stable. That's because we need this additional condition because we are looking at an infinite time horizon property. I'll now give some miscellaneous insights and I will stop. I think I have already gone a little beyond what I budgeted for myself, but I think these are interesting insights, so I'll share them. There is a very interesting property called decoupling. So let's look at L nodes. We looked at one node and we pulled out one node, but instead of one node, let's tag L nodes. If you look at these L nodes and if you remove one of them, for example, this doesn't contribute that much to changing the empirical measure, this one particular node. In some sense, that's the weak interaction that we have here, and we are leveraging that property. So if you remove this one node, the empirical measure doesn't change. When you remove L nodes, the empirical measure doesn't change. The empirical measure is roughly going to be something that is governed by the generic law and the field associated with that. Now, if you look at these L nodes which have been extracted, the field is fixed. The interaction of these L nodes was only through the field, but if the field is fixed, then these are essentially executing a Markov process with respect to the field that's governed by the empirical measure. And so the evolution of x1 up to xl in some sense is asymptotically independent and identically distributed and given by the q that govern the field. So one can, which is the solution to the level 4 fixed point. So one can actually get this interesting decoupling property. And if you recall the independence assumption, that was exactly this decoupling property. So that was an additional assumption that was needed, and thanks to this mean field and weak interaction, we actually have this independence property, which puts our heuristic in a somewhat more firm ground. But one needs rigorous analysis, and that has been done. But here, I'm just saying that there is additional evidence that it can be put on firm ground. Next question is a large deviations question. So here are n particles, they're all interacting with each other. The Q, that is the solution to the fixed point, is the right Q. Let's say that evolved in this way. What is the chance that the law of n particles, the empirical measure, looks not like Q, but like some other R? So one could ask this question. One can answer this question as well. It's like Sarnoff's theorem here. The probability of this empirical measure looking like R is like e to the minus n times the relative entropy. So what is that relative entropy? So if these nodes are behaving as if the law is R, then the mean field is something that comes from this R. And then you look at the response associated with that, which is T of R. So the normal behavior for R is T of R. And for you to be in a encounter a situation that is empirical measure R is a very low probability event, and the probability is given by e to the minus n times the relative entropy between this empirical measure, this measure R, and the nominal. It's just that the nominal should come from the R itself. So the probability that you will see an empirical measure in the neighborhood of R is e to the minus n times the relative entropy between R and the norm, the response for this R. Okay. Now, from here too, you can actually get back the fixed point because the limit law, which is the Q that one looks for, which solves the fixed point equation at level 4, is the R that has relative entropy equal to 0. And if relative entropy between R and T of R must be 0, then it must be, these two measures must be the same. So it's the R that satisfies R is equal to T of R. That's the fixed point. So one can get to the fourth level fixed point this way as well. But one can prove this large deviations principle as well. Another large deviation principle is what's the chance that at stationarity, the n nodes distribution looks like nu. And one can write that as e to the minus n times v of that nu. The v is a suitable function. And in particular, that if you look for the point where it is 0, that point is actually the equilibrium point. So remember the globally asymptotically stable equilibrium and a xi. So it would be that particular point. And one can write a large deviation principle for the stationary measure or invariant measure as well. What's more, that V actually satisfies the second law of thermodynamics. It's like the entropy function or relative entropy function, and it's always negative. So the negative of this is always increasing. That's the second law of thermodynamics. One can generalize these results to the more general case. Globally asymptotically stable equilibrium requirement can be relaxed. There are some other but simpler conditions, and you allow for multiple equilibria and so on. And in that situation, we can also find out what are the times for which you will remain near one equilibrium, exit times. You can characterize all of these for the empirical flow. Okay, so with that, I will stop. I will leave this particular slide, which captures the 4 levels once again for you to look at as we go through the questions. Thank you very much.
Okay. Thanks a lot, Rajesh. So I think before any questions, and I forget, let's all unmute and thank Rajesh for the wonderful talk.
If I may stop sharing, I can then look at you and answer if that's all right.
Yes,